In continuation with the last lecture on software testing, where we mainly discussed black box testing methods, now we will discuss some of the white box testing methods, and let us see what the techniques are and how you derive your test suits and different test cases through an analysis of the code. So, let us first look at what are the different black box and white box testing techniques, and it is an overview of these two different techniques with a comparison. So, in black box testing, basically modules are first tested externally from the point of view of the externally observable behavior. So, the tester uses the external interface for testing, and in white box testing as opposed to the black box approach, the tester has the knowledge of the code. So, in a black box method, you do not know what is there inside. So, given a module, if you want to test the module, the tester at the code that the module contains, but basically the specifications or the contracts that are supported by the module. So, based on the contracts or externally observable behavior, the tester derives the test cases and tests these modules in the black box fashion. But in white box technique, the tester looks at the code and then derives the test cases. So, in a white box method, basically the test cases do not get derived from the high level specifications or the functional requirements. You are mainly looking at the code, the structures, the usage of variables, different control paths, data flow paths and so on. So, thus tester has knowledge of code in white box testing, and test cases are generated to test the coding structures. These are the main differences in black box and white box approaches. So, this slide summarizes black box testing techniques, which are external testing techniques. For example, first one is the functional or feature testing. We also have seen boundary value testing, where you mainly look at the boundaries of the different parameters that you pass to functions and find out whether the module works with the extremes, and also check for the behavior beyond the extremes. Then test for absence of features. So, for example, whether a given feature or a use case has been supported or not, that can be found out through black box testing measures. So, you typically use specifications to generate the test data, and then white box testing, which is mainly internal testing. So, the difference is mainly from internal or external perspectives. So, this is also called structural testing, because the internal structure is used to generate test data. So, typically it covers tests for statement coverage, conditional branch coverage, different paths in the control flow of the program or the module, but this does not detect absence of features in the software. For example, if we look at a module which has a while statement and which mainly covers a specific feature, you will be mainly not looking at the feature for which the while statement has been programmed, but you are mainly looking at the conditions and applying certain criteria which we are going to see and deriving these test cases. So, we have a few examples for the feature, how this white box testing criteria may not detect absence of features in the software. So, for that we have an example in later slides. So, let us continue with our coverage criteria and explore more about these white box testing techniques. So, let us look at statement coverage first. So, what statement coverage says is that you select a test suite such that each statement in the program is executed at least once. So, if you have a program of 5000 lines, your test suite that satisfies the statement coverage criteria will generate as many test cases as required to cover all these statements. So, if you have 5000 lines of code, you do not require 5000 test cases to cover all the 5000 lines of code. You might be able to do or cover these statements with lesser number of test suites. For example, if you just have a single sequence without any branching, just one case may be enough to cover all the statements. So, what is the motivation for this particular criteria? Why do you go for statement coverage criteria? So, this is basically from the fact that an error may get masked if tests do not execute parts of the program. So, for example, if you are not covered all the statements, you might be actually hiding an error which may be because of those statements that have not been covered by your test suites. So, a statement coverage criteria guarantees that all statements in the program are covered at least once. So, when we say all statements, we basically mean all elementary statements. So, what are the elementary statements? You can find them out from the syntactic definition of the language that you are using for programming. So, for example, an assignment statement is an elementary statement, a procedure call, an IO statement in the conventional block structure languages, for example, printf, scanf. So, these are the elementary statements. All of them should be covered at least once. So, as we have seen, this slide summarizes that a test case may cover many statements, and one may try to minimize the number of test cases such that all statements are still covered. So, how do we reduce the number of test cases and try to cover as many statements as possible? So, it is not required that you have as many test cases as the number of statements in the program. You can cover all the elementary statements with a fewer test cases. So, what is the criteria? What are the techniques? Let us continue and let us find out answers to these questions. So, here is an example for statement coverage. So, this is a function that calculates Fibonacci at place n, integer n, Fibonacci integer n, and it is defined on n 0 or more. So, let us look at this code. So, you have an if statement, if n is less than 2, then you return n, else if n is greater than or equal to 2, you recursively apply this Fibonacci, and so you calculate Fibonacci n minus 1 and then you add to it Fibonacci n minus 2. So, which are the elementary statements in this? Is this if statement elementary statement? So, this is not an elementary statement, this is a branching statement, but this return n, this is an elementary statement or basic statement in this in the terminology of statement coverage, and this is another return statement which is also an elementary statement. So, what the criteria says is that you must be able to cover all these elementary statements through your test suite. So, is it possible to cover these two statements within with one case itself? If you look at the first condition, it is n less than 2. So, that means this is for n greater than or equal to 0, this will be satisfied by 0 and 1 values against the values of n. And if you look at this else part or this return the number by recursive computations of Fibonacci n minus 1 and n minus 2, and here the condition is satisfied by a value of n to be greater than or equal to 2. So, you cannot get one test suit to cover these two statements, require two, at least two cases. So, 2 are enough. So, for example, here the green box below gives one such test suit, n is equal to 3 and n is equal to 1. So, this test suit contains two different test runs. So, you have to execute this program twice, first with a value of n to be say 3 and then with a value of n to be 1. So, if you execute this program, this Fibonacci function with n to be 3, this else part will be applicable and you will cover this second elementary statement, whereas if you execute this program with the value of n as 1, the first elementary statement will be covered. So, this gives you the statement coverage criteria. So, this is an example of statement coverage. Now, let us look at some of the observations. So, we say that missing features do not get detected. So, how come? So, are there missing features? For example, in this program, if number supplied is negative, the function does not report an error. So, there is no feature in this function to return with an error if the number supplied is negative. So, that feature will not get detected, because our coverage criteria, if you look at, mainly is from the point of view of covering what the statements are there. What is not there, it's not covering. So, if you are able to cover these two elementary statements, you satisfy the statement coverage criteria. So, even otherwise black box measures will not be able to detect missing features, and this is an example that we had promised. So, if the number supplied is negative, the function does not report an error, and if this is a wanted feature, but which is missing in the software, this we will not be able to detect through statement coverage, because such a test case is not generated through this particular coverage technique. We are only mainly worried about covering the statements which are there, and then we do not cover implicit statements. So, what are those implicit statements? Example is on the next slide. So, we have here another function, a flip function, which takes in a Boolean variable and returns a Boolean result. So, this function is intended to flip the variable and return the flipped Boolean value. So, what is expected with flip true is false, and the expected result on flip false is true. So, let us look at the code that we have for this flip statement, and let us see what happens when we apply statement coverage criteria. So, you have declared a Boolean local variable. So, what you are saying is that if var, whatever comes in, if var is true, then first assign false to local and return local. So, this is just an example. Now, you have two elementary statements here. This is one assignment statement and the return statement. So, local equal to false is one elementary statement, and local and return local is another statement. So, in order to cover local equal to false and return local, you have one test suit which is enough. So, if you have var to be true, this assignment will get executed, local equal to false, because if Boolean value var is true, then this is true predicate will evaluate to true, and the local equal to false assignment will get executed, and you will be able to see the correct return value to be false. So, var equal to true is sufficient to cover all the statements, but the error that flip does not work with var equal to false is not detected. So, why does this not get detected? The reason is that we have overlooked the else part. So, when you have this if statement, you also have the else part which is implicit here. So, we have to also cover that implicit part. So, the next slide gives you the implicit else statement. So, if you look at the code, we have also added now the implicit statement, and this program and the program on the earlier slide are equivalent. So, you have else do nothing. So, and simply return local. So, if you have false, and if you say that the value of local is assigned to one default, this may not work correctly. For example, test suite var equal to true is not sufficient to cover all statements. Now, if you assign local equal to var in the first statement, and if you simply return local as it is, then you will not get correct value. For example, I will make a small change on this slide, and you say here local equal to var, and let us look at this program now. So, if you assign the initial value of local to be var as it is, and then you will be returning local as it is. So, if you execute this with false, you will return false. So, test suite var equal to true is not sufficient to cover all statements. Error that flip does not work with var equal to false will get detected with this test suite var equal to true, var equal to false. So, now if you want to cover this statement, you need to execute this else part, and in order to execute else part, var should not be true. So, that gives you another input value for this parameter var to be false. So, if you have this test suite, then you are able to cover all these elementary statements. So, basically this assignment statement and the second else part, both of them you are able to cover if you use the second test suite. So, in the last slide, if you have since the program does not contain the else part, you might overlook that else part and not you might not generate the test suite to cover that statement, and then that results in an insufficient statement coverage criteria, and you will not be able to detect the error. So, if you also look at the implicit statement, the implicit branches, and apply the statement coverage criteria, you are improving on your statement coverage, and you will cover errors that get resulted due to such implicit statements now which are not seen in the source code. Now, we will move on to another technique after seeing the statement coverage criteria, which talks about path based testing. So, basic path testing. So, what are the basic paths in the program, such that if you cover these basic paths, you will be able to cover all the statements in the program. So, in this basic path testing method, you select test suite such that the basic paths are covered, and this guarantees that every statement gets covered. So, let us look at this path based criteria and link it to statement coverage. So, you basically have representations for elementary statements such as assignments, IO, call, then conditional statements such as basically the if then else statement, and you may also have the case statement, then conditional loops, while, do and repeat until, and sequential composition of two sequential statements. So, now these are the primitives that give you variations in the control flow of the program, and you can generate the control flow diagram of a given modular program, and then go through different paths and see how many paths you should test. In other words, how many test cases you should generate, so that you cover the basic paths, and then all these basic paths lead to coverage of all the statements in the program that you are testing. So, let us look at some of these primitives that are used to generate these control flow graphs. So, first is the sequential composition. You have two statements. So, here is one example. You have S1 which calculates interest as balance into some x percentage factor, and S2 as balance equal to balance plus interest. So, you add this interest into the balance. So, you have S1 followed by S2. So, this is your sequential composition, and if you just have only these sequential statements one after the other, S1 followed by S2 followed by S3 followed by S4, then that would mean that you just need to have one test suite, so that you can cover the entire all the statements in the program. So, you have only one path and you will have one test suite here, if you have just only the sequential composition. Then next we need to look at the branching statement. So, for example, you have a code on the slide. If employee dot performance is high, then you apply one incentive equal to x, some value x, else incentive is x by 2, and then print employee ID, employee dot ID and the incentive. So, you have 4 statements here, S1, S2, S3, S4, and this is your equivalent flow graph. So, you have from S1 is a branching node, from S1 you can go to S2 and S3 and you then come back to S4. So, S4 is after the if then else. So, S4 executes after the entire if then else statement executes. So, it is basically is a join point, or it is a join of the 2 branches, and S1 is the 4th point where you branch into 2 different paths. So, else part is the S3 part and the if part is the S2 part. So, in this, for this particular flow, how many test cases do you require, so that you cover all the statements? You will require 2 test cases, so that the one path is S1, S2, S4 and the another path takes covers nodes S1, S3 and S4. So, you have 2 basic paths in this program, and which you can for which you can test, and that will result into the statement coverage criteria, including all the paths that get generated due to all the possible branchings at this particular condition node. Now, this is the while statement. So, in while statement you execute a condition at the beginning of the while loop, and while that condition is true, you continue to execute the body of the while loop, and at the end of the while loop the condition evaluates to false, you terminate the while loop, and then the program continues. So, in this slide we have 3 statements, and so you are processing a file. So, while it is not end of file, you read a value from file and print it, and when the end of file is reached, the statement gets terminated and you continue with the program. So, S3 is the next statement. So, it is basically you can see that it is a sequential composition of S1, S2 together as while loop, and then S3 at the end of the while loop. So, S1 is your conditional statement, from where you can go to S2, and from S2 you come back to S1 to check the condition. So, it can be seen here from this figure that in while loop you first check the condition. So, typical this is a usage. When you open a file, you first want to check whether before reading, first want to check whether you have already reached the end of file. If the file has no input, you will not want to read the value from that file. So, you have to check before you execute the while loop body. So, this is a typical usage where you want to first check for the condition and then continue. So, from S1 we can see that you can, so S3 is the termination of the while loop, or the last it is outside the while loop. So, once you reach S3 you continue with the rest of the program, and S2 is your body of the while loop. So, we have now combined these 2 statements into one S2 itself, because adding one more statement here will not make a difference to number of paths, because it is the same path. In the same path itself, if you have these nodes, you can merge them. So, we come back to S1 after we read the value from the file and print it, and check the condition again, and if the end of file has not been reached, you continue with the body of the while loop, else you continue to S3, you terminate while loop and continue with S3. So, this is your while statement, and in order to cover these statements, how many test cases do you need? First is to go into the while body, and the second test case to terminate the while loop. So, you require a file which has nothing in it, where end of file will be the beginning file pointer itself, and then a file which has a few items in it, which will be able to go through at least one. So, one item in a file is good enough to cover all these statements. So, a file with one single item and file with nothing in it, an empty file can be used to cover these basic paths, which are 2 in this particular case. Now, let us look at the case of a repeat statement. So, this is your repeat statement. So, we have some code here. So, we assign a value x to temp 1 and then x square to temp 2 and set I to 0, and then repeat x equal to x plus temp and also increment the I count until x becomes equal to temp 2. So, that means we are showing that by adding the value of x again and again, you can generate the square. So, and then at the end of, once we come out of this repeat loop, we print the value of x and I. So, we know that we need to we can repeat it until this becomes a square of itself, and this then at the end of the loop we print the value of x and I. So, this is your repeat statement, and if you want to cover the all the statements, you need to take again this one particular path and then another path from S1, S2 to S3. So, we can see that this can work for values. This will not work for all the values. So, if the value is just 1, then the x will get added to itself and the value will become 2, and you may never terminate this loop. So, this criteria gives you all these paths, but if you choose that test. So, if 1 is the value of I is value of x to be 1 is good enough, but then once you get into this particular statement, you might not come out of this. But at the same time, so if it is stated that this loop works for this particular set of values, then you will be able to at least cover these paths. So, you can see that these criteria are not perfect, and they may not still detect all the possible errors. For example, boundary value analysis is not done in this, and typically you are mainly looking at only the structure of the code and the available statements and the available branchings. So, through them you are covering the test. So, in this repeat statement, this is the diagram, or this is the flow graph of the repeat statement. So, coming back to our flow diagrams and how to compute the basic paths. So, you have this S1, S2 and S3. So, S1 is your basic statement where you are incrementing x with temp and incrementing the value of I, and then you are going to S2, and you can see that S2 is the branching node from where you have 2 outgoing edges, whereas S1 is your elementary statement, and from S2 you can come back to S1 or you can jump to S3. So, until you get the square, you continue, otherwise you slide to S3 and continue your execution after the repeat statement. So, here we can see that there is once this path from S1, S2 to S3, and in order to cover this particular edge, you need to take choose a test case such that you cover S2, S1, S2 and come back to S1, and then perhaps take S2 again, and then through S3 you come out. Then we will look at another possible statement in programming languages such as C, C++. So, you have this switch case statement where you have many choices at the switch node, and you can fork into many choices and then join later. So, for example, here you have a choice. If the choice is T, then you prepare T. So, drink equal to prepare T and then terminate the case statement. Another case is if the choice is coffee, then you prepare coffee. If choice is juice, you prepare juice, and so on. So, you have these 3 different cases, and this is your branching. S1 is the branching statement, or the branching predicate from where you find out what the choice is and then branch to appropriate nodes, and then you join at S5. So, S5 is your serve drink, or it's actually the termination of switch loop, and I have combined the serve drink with that because it's in sequential composition. You need not I have to point out all the nodes. So S5 can be your serve drink, which is the end of your switch statement. So here if you want to cover all the statements, these are the basic paths: S1, S2, S5, S1, S3, S5 and S1, S4, S5. So this is the flow graph for a specific switch statement. And then if we look at a compound condition, so typically say if A or B. So in this example, we can see that we have a compound condition. So we are looking at two values, and we want to execute x if A or B is true. So if A is true, we will execute x. If A is not true, if B is true, then also we will execute x. If both of them are true, then we will again execute x. Else, otherwise something else will be done. So if A and B both are false, then something else will be done. And this is the compound, the flow graph for this compound condition. So this is your S1, which checks for A. So if A is true, we execute x and then join at the end of the conditional branching statement. So the last node is the joint point of this compound conditional statement. Now if A is found to be false, then S2 checks for B. So B could be false or true. So we have a branching here. So we have the first branching at A. If A is true, then execute x and we can continue. So we don't need to check for B. If A is not true, then the lower path is taken. So in S2 we check for B. If B is true, then we execute x and then we join at the end of the conditional statement. And if B is false, we execute y and then we again join at the end of the conditional statement. So in this case, we have this flow graph where we have two branches. So this is an example of a compound condition. So we need to carefully look at these compound conditions and formulate the flow graphs. So otherwise we will miss some of the branches, and then they become implicit and then you do not cover for them, and that will result into errors getting undetected because of not covering all the basic paths in the control flow graph of your program. So now here we will look at measure called cyclomatic complexity and see how that gives us a clue to generating these basic paths. So so we have looked at all these basic statements and their flow graphs, and in a typical in a big program you have to analyze the entire program and generate the flow graph of this of your given program, and then find out how many paths in the entire flow graph should be tested, so that you will cover all these all the statements of the program, so that you can satisfy your statement coverage. So typically a program includes many branches and many statements, and you may have many such paths. So you need to cover the paths. So how many cases are required? We have to reduce the number of cases, but we should also make sure that all the statements get covered. So there is a measure called cyclomatic complexity, and that measure actually tells us how many paths we need to generate, so that this our criteria is satisfied. So cyclomatic complexity gives number of independent paths in the basis set, or the basis set for these paths for this statement coverage is that which has the very basic independent paths, so that each path gives you at least one covers at least one extra edge in the flow graph. So they are not that means they are not redundant. So it gives upper bound on number of tests that must be conducted to ensure all statements get covered at least once. So this could be computed as number of regions. So in that you count outer region also, a number of predicate nodes plus 1, or you can count it as number of edges minus number of vertices plus 2. So that is your number of regions. So you can see that cyclomatic complexity for this compound condition which we had just seen a couple of minutes ago can be computed here to be 3. So, if you look at this flow graph, so we have this A. At A we have a branching. If A is true, we are going to go and execute X, that is we are going to take upper path. If A is false, then we will check if B is true, then we will take the middle path and we will go via this X. Else if B is not true, then we are going to take Y. That means if A is not true and B is also not true, we take the bottom path and then we join here. So, we have this one region which is this one which over which the mouse, I am rolling the mouse, and then this is the middle region and you have the outer region. So, these 3 regions give you the count of the number of regions, give you the cyclomatic complexity. So, you can calculate as number of predicate nodes plus 1. So, you have this one node and this another node. So, you have 2 branches. So, this number of predicate nodes plus 1. So, 2 plus 1 equal to 3, or number of edges minus number of vertices plus 2. So, number of edges, how many edges are there? This is 1, this is second, third, fourth, fifth, sixth and 7, and number of vertices is 1, 2, 3, 4, 5 and 6. So, 7 minus 6 plus 2 and you get 3. So, basis set has 3 paths. So, if you have 3, so we know 3 paths, and then if you have these 3, if you take these 3 paths, so you take this conditional and then take one branch and cover it, then go to another branch and at this conditional take one branch and cover it, and then for the second one cover other branch as well and keep the earlier one as it is till here. So, you get this one path, top one, this is the middle path and the lower path. So, this is your basis set, and these 3 paths if you cover, you are able to cover all the statements. So, this is your cyclomatic complexity example, and it will be interesting to see that if you, even if you have very too many statements and many paths, this number of regions that you have could be small, and with this basis set, this gives you the upper bound, and so these many paths you need to generate. So, how do you generate these paths? You have to select the values such that these paths get covered. So, you have to select appropriate values of A and B. So, this next slide tells you what are these values. So, if we look at this example again, so 3 independent paths are as follows: A is found to be true, and then A is not found to be true, but B is found to be true, and A is not found to be true, and B is also not true. So, test suit is the following: A is true, B is false. So, we have chosen B to be false here with A is true, but it does not matter. Then A false, B true is another test, and test number 3 is A is false and B is false. So, these 3 tests can cover all the statements. So, these 3 tests give you the 3 basic paths in this particular example. So, and this is just the statement. So, if you have this statement, which is which you can find at the bottom of the slide, if A or B, then X else Y. If you have this statement, you require 3 test cases such that you can cover all the paths, but in this control flow graph, and then that all the basic paths in the that is independent paths in the basis set, and then that results in covering all the statements in the program. So, if A or B, then X else Y. To test this, you require 3 test cases, which may not be apparent if you just look at the statement. You might think that you need to execute then part and else part only once, but if you look at this, there are 3 possible independent paths. So, this close analysis reveals the different basis, the paths in the basic paths in the basis set, that is the independent paths, and you need to select appropriate values such that the basis set gets covered, and that results in statement coverage. So, are the independent paths in the basis set unique? So, they need not be unique. In this example, of course, you have these 3 paths, but you can construct various examples, or you can construct programs. In general, you can cover through different basis paths in a bigger program, and I will leave it to you as an exercise. So, try to write a program where there are different ways to construct the basis set, or to construct the set of independent paths. So, say take 4 paths and then see whether you can construct 2 examples that has exactly 4 independent paths in the basis set, and you have two different basis sets. Now we will look at another criteria for white box testing. In condition testing, we mainly approach from the point of view of the composition of conditions. So, here we can see that we can have simple conditions or compound conditions. So, how to approach these conditions? So, testing is basically white box testing has been covered in great detail in literature, and there are many different approaches and ways to design your test suite based on white box testing. So, you could do a very exhaustive testing, but it won't be possible due to simply extremely very high very large number of test cases. So, exponential number of test cases. So, it won't be possible to cover exhaustively for all possibilities, and you will have to execute literally the program for all possible cases through. So, for example, you if you have a loop, you may not know how many times you need to execute the loop for a specific value. If you have say loop from 0 to 100 for a specific value, the loop may not execute correctly. So, but still, so all of exhaustive testing may be impractical, but still these coverage criteria gives us certain level of confidence, and there are many such different methodologies and methods, basically approaches to white box testing which you can find in literature. So, we looked at these various criteria for statement coverage, and then we looked at the approach from cyclomatic complexity point of view, and now we will mention a few approaches from condition from the point of view of conditions and composition of conditions. So, if you look at conditions, they are mainly classified as simple conditions or compound conditions, and a simple condition is typically a Boolean variable, or you could also have relational operators such as say a less than b, a greater than or equal to, less than or equal to, or a equal to b, and so on. And a compound condition has composition of two or more simple conditions, two or more even compound conditions. So, a compound condition can be complex, and the composition is done through typically Boolean operators. So, error could occur in conditions due to wrong variable values and wrong choice of operators, wrong expressions inside the conditions, and parenthesis problems. So, there could be parenthesis problems where the parentheses are not closed appropriately, or they're closed at inappropriate places. So, condition testing looks at basically conditions and analyzes the different compositions and derives test suites based on the conditions. So, for example, you could have a branch testing policy which says that you test for true and false for C. So, you have a condition C, test for true and false for C, and make sure that every simple condition in C is executed at least once. So, this criteria could be designed for your approach from point of view of composition of conditions and conditions. Or you could take a more exhaustive approach and say that if you have a Boolean expression with n variables and test for all possible 2 raised to n values. So, this gives you all possible values. For example, if you have A, B and C, and so we will just make a simple table. So, you have these 3 Boolean variables. So, how many values can you generate for as your test suite that satisfies this criteria of domain testing, that is test for all possible 2 raised to n values. So, you have here 3, and you can generate 8 different test cases for this conditional coverage criteria. So, this is more exhaustive, and you need to generate all possible values and many times it's not possible to test exhaustively for a large program. So, you reduce your criteria, and based on these, basically the path based criteria are quite common. So, if you have these Boolean expression, you can generate these test suits with different with these values of all your Boolean variables, and simply generate your test suit through a table. And if you have relational operators, for example, if you have A or B, so less than or equal to B and so on, test for A less than B, A greater than B, and A equal to B, so that you are able to cover the implicit paths as well. So, condition testing strategies look at mainly the conditions in the program, the branching, the conditional predicates and composite conditions, and the approach is from the point of view of conditions and their composition. So, this is another approach to white box testing, and then there are various other approaches. So, we will also mention data flow testing strategies. Basically, you select paths based on the data flows. So, you find out where a definition, where a data is defined, and where it is used, and based on that definition use chains you form, and you try to cover DU chains at least once. So, where data is defined and where it is used. So, if it is defined in one statement, and if it is used in two different branches, you must take that definition and take its and generate test paths such that both the usages are covered. So, this is another approach, and it's mainly from the point of view of data flow. So, there have been such many approaches you can find, and test oracles could be built to analyze these your programs and automatically generate test cases, and then the validation criteria have to be satisfied, and when the tests when you run your programs through these test cases which satisfy some of these criteria which we just discussed, you have to validate the output, find out whether the given output, the generated output is as per what is expected. So, one can write such or use the tools to analyze the programs and generate the tests, and which also automatically test these programs against the test generated. So, we have seen through these different the different examples in slides how you can approach testing from structural point of view or white box point of view. We are mainly looking at the structure of the program, different conditions used, different the branchings, and the looping constructs, and the composition of sequential statements, and the program has many such, and if you approach from the basis set or the independent paths point of view or the cyclomatic complexity, you will be able to cover all the statements. So, but we have also seen that it does not detect, it may not detect still errors might still be still go undetected, because say for example absence of features and so on. So, now we have an example program for you, and on this slide you can try different strategies on the below program, and make a few errors and then try the test again. So, not only this program, but you could take any of your programming assignments, data structures, or algorithms course, or your database course, or any operating systems and so on. So, take any of your programming assignments which you are which are coding or which you have coded, and then apply these criteria and test the program. So, in order, you probably have not been applying any of these methods formally. So, some of these techniques you should try to apply and see whether by applying these test cases will you be able to detect the bugs. So, if you find a bug, you go and try to apply some of these techniques, white box and black box techniques, and then by through that see whether you are able to detect your bugs.